This video provides a brief overview of the Mile High Flood District's Detention Basin Design Workbook. My name is Derek Rapp, and I've worked closely with the Mile High Flood District over the years to develop and update the various software programs they provide. When you open the Detention Basin Design Workbook, you will automatically be directed to the intro worksheet. This is version 4.03, released May 2020. Always check the district website to make sure you have the most current version before starting a new project. You can also click on the History button to see recent updates that have been made to the workbook. This workbook uses a modified pulse reservoir routing method to design and/or review a detention basin. It works with both existing facilities and proposed designs. The workbook can be used for an extended detention basin, a retention pond, a constructed wetland pond, a sand filter, a bioretention rain garden, or even for an underground detention facility. The workbook is broken up into two primary steps. First, on the basin sheet, the program will approximate the stage area volume relationship for a detention basin based on user-defined watershed parameters and basin geometry preferences. A known stage area volume relationship based on site grading plans can also be input directly by the user as opposed to the more generic geometry developed by the program. Second, on the outlet structure sheet, the program will determine the stage discharge relationship based on the user-selected outlet types and configuration. It will then route storm inflow hydrographs through the detention basin using the modified pulse reservoir routing method to generate discharge hydrographs for comparison against allowable pre-development release rates. Below are some quick links to various worksheets within the workbook. First, we will provide a brief overview of the basin worksheet and development of the stage area volume relationship. The first step is to select the BMP type you are evaluating from the pull-down list. Depending on the BMP type selected, several default inputs, such as the water quality capture volume, will automatically populate. Next, you need to provide the tributary watershed parameters required to run the Colorado Urban Hydrograph Procedure, or CUHP. These inputs include area, length to centroid, slope, imperviousness, and a breakdown of soil types to calculate default Horton infiltration parameters. The last required input for this section is selecting the appropriate rainfall depths from NOAA Atlas 14. One of 45 different locations within the district can be selected from the pull-down list, and the corresponding 1-hour rainfall depths for each recurrence interval will be shown here. Or you can provide your own rainfall values by selecting user input at the bottom of the list and manually entering the values over here. Once all of the inputs have been provided, the workbook is ready to generate runoff hydrographs for the tributary watershed. By clicking the Run CUHP button, the CUHP code will run within this workbook and generate runoff hydrographs for the tributary watershed. After CUHP is run successfully, the total runoff volume for each recurrence interval will populate in these cells. The complete runoff hydrographs and peak flow results are presented on the outlet structure worksheet and will be discussed later. Based on the calculated CUHP runoff volumes for each recurrence interval, approximate detention volumes are calculated using empirical equations. These results provide a starting point for sizing the basin geometry. The next step is to define the storage zones you want to include in the design and provide basin geometry constraints. At a minimum, you are required to select at least one storage zone. The Zone 1 pull-down list includes several design options starting with water quality capture volume and going up through the 100-year storage volume. It even includes a user-defined option to override the volumes calculated above. Next, you have the option to select storage volumes for Zones 2 and 3. The zones are configured like layers of a cake, as seen in this image for a standard, full-spectrum extended detention basin design. Zone 1, in dark blue, represents the water quality capture volume, or first layer of the cake. Zone 2, in light blue, represents the second layer of the cake, which is equal to the EURV minus the WQCV. Zone 3 at the top represents the third layer of the cake, which is equal to the 100-year volume minus the EURV. Once you have defined the different zone storage volumes, you can move on to providing design constraints for the basin geometry. The required inputs will vary depending on the BMP type selected above. The initial surcharge and trickle channel inputs only apply to an extended detention basin. The others are applicable to all BMP types. Once all of the required inputs have been provided, the program will automatically begin calculating the basin geometry necessary to satisfy the required storage volumes. It will then generate the full stage area volume relationship. A summary of the calculated basin geometry is provided in the cells below. The complete stage area volume calculation table with stage increments of hundredths of a foot is hidden at the bottom of the worksheet and can be reviewed by clicking this button. However, a condensed stage area volume table at a default stage increment of tenths of a foot is shown on the main part of the worksheet, along with figures of the stage area volume relationship. At this point, you have completed the basin worksheet and are ready to move on to the outlet structure worksheet. It should be noted, however, that for existing detention facilities with as-built grading information, or for final designs with proposed site grading information, you have the ability to enter your own user-defined stage area relationship in the blue columns. The user-defined stage area volume relationship overrides would then be carried over to the outlet structure worksheet instead of the program calculated geometry. That completes the brief overview of the basin worksheet. Now we will provide a brief overview of the outlet structure worksheet and development of the stage discharge relationship. When opening this worksheet, the estimated stage and storage volume for each zone selected on the basin sheet will automatically be carried over, shown here. The first step on this sheet is to select the outlet type you would like to use for each zone. Options include filter media for rain gardens and sand filters, an orifice plate or elliptical slot to drain the water quality capture volume and excess urban runoff volume, and flood control outlets like a vertical orifice or an overflow weir and outlet pipe. Depending on the outlet type selected, some default input values will automatically populate, and other input cells that are not relevant will be grayed out. Also, only the sizing buttons that are relevant will be visible. We will now go through each of the outlet type sections below, but know that you only need to provide inputs for the outlet type selected. The first section includes input cells for the media filter with underdrain. Here, you need to provide the depth to the orifice invert and the orifice diameter. You also have the option to allow the program to automatically size the orifice diameter to match the target drain time. The second section is for a water quality outlet plate, which can be either an orifice plate or an elliptical slot. Regardless of type selected, you need to provide stage values for the bottom and top of the plate. If an orifice plate is used, you also need to provide the orifice spacing and orifice area per row. If the orifice openings are evenly spaced and the same size, you can just enter the values here. However, if the orifice openings are different sizes or spaced unevenly, you can enter the unique values in the table below. If an elliptical slot is used, the input cell descriptions will change and you will need to provide the slot height and gap width in these cells. Depending on the zone selected, you may have the option to click one of these buttons to help size the openings in the water quality plate. The next section provides input cells for a standalone vertical orifice, such as an opening in the side of a concrete vault. The opening can be either circular or rectangular in shape. The inputs include the orifice invert stage and orifice dimensions. Two separate and independent vertical orifice openings can be entered in this section by using both columns. The next two sections typically work together for flood control and represent an overflow weir with grate at the top of a drop box structure and an outlet pipe with a flow restriction plate at the bottom. Two drop box structures in series can be evaluated by filling out both input columns. Input values for the overflow weir and grate include the height of the weir, the length of the weir on both the front and the sides, the slope of the overflow grate, and the percent open area of the grate. You can also evaluate the impacts of debris clogging the grate. Input values for the outlet pipe and restriction plate depend on the type selected at the top of the worksheet. The input values required include the pipe invert stage and the restriction plate opening dimensions. Depending on the zone selected, you may be able to use one of the sizing buttons to help you size the outlet pipe restriction plate to control the 100-year release rate, and to size the overflow weir width. The last input section is for an emergency spillway capable of conveying runoff in excess of the design storms, or if the outlet structure becomes clogged. Here, you need to provide the spillway crest stage, width, and side slopes. You can also enter the desired freeboard depth. Once all of the relevant inputs have been provided above, the program will automatically generate a stage discharge relationship for the outlet structure, and then route the CUHP inflow hydrographs through the basin to generate discharge hydrographs. The complete tables are hidden below and can be viewed by clicking these buttons. A summary of the results is shown in the table. Any values that have been overridden will be flagged by highlighting the cell pink. Also, any results that do not meet criteria will be highlighted pink. The first 7 rows in the table are based on the inputs from the basin worksheet and the CUHP generated hydrographs. The results include the rainfall depths, CUHP runoff volumes, and pre- and post-development peak flow rates. It should be noted that you have the option to override the CUHP results with your own inflow hydrographs and peak flow rates. The pre-development peak flows can be overridden directly by entering the appropriate values here. The inflow hydrographs can be overridden by scrolling up and to the right of the figures and entering the new values there. If you do, the values in these rows will update to reflect the user input volumes and peak flows. The remaining rows in the table show the results of the modified pulse routing method calculations. The peak discharge for each design storm is shown in this row, and the ratio comparing the discharge to the pre-development level is shown here. The next row identifies which element of the outlet structure is controlling the release rate for each design storm. This is very useful in identifying if the design is functioning as intended. These rows provide a check on the velocity through the overflow weir with grate to make sure they don't exceed 2 feet per second. These rows show the drain time for each event. Be sure to check that the appropriate drain time for the selected BMP type has been achieved, and that the 5-year event drains out in less than 72 hours. The last 3 rows show the actual routed results for stage area and volume, as opposed to the estimated volumes determined on the basin worksheet using empirical equations. The values in this summary table should be used for the preliminary design. Up and to the right of the figures are the CUHP-generated inflow hydrograph values used in the modified pulse routing. You have the option to override these CUHP hydrographs by pasting your own values into this table. Also, up and to the right of this table, there are some inputs that allow you to export the calculated discharge hydrographs from this workbook to a separate workbook for later use. The last part of this worksheet allows you to create a specific stage area volume discharge table at desired stage increments. This is very useful for generating report tables. That completes the overview of the outlet structure worksheet. Now we will quickly look at the remaining worksheets in the workbook. The reference worksheet includes helpful information including figures depicting basin geometry and outlet configurations, as well as explanations of various equations used in the workbook. You can also reference the Urban Storm Drainage Criteria Manual for more detailed information. The User Tips and Tools worksheet provides links to videos like this one, as well as several other helpful tips for commonly encountered situations. At the bottom of the sheet is a tool to help back calculate an approximate stage area relationship from a known stage volume relationship. The last button here takes you to the BMP Zone Images worksheet, which includes figures that demonstrate various zone configurations and the corresponding outlets for the different BMP types included in the workbook. That concludes our overview of the Mile High Flood District's Detention Workbook. Please check out our other videos with more detailed information on the basin and outlet structure worksheet, including some practice examples and commonly asked questions.